Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about mass defect and binding energy. So hopefully, you have a basic understanding of what the mass defect is, what is the binding energy, what is a unified atomic mass unit, etc. Okay, so there are a ton of values in your data booklet so that you are aware they exist. So hopefully you can use that for doing your calculations. So in this video, I am going to do example 1 and 2 since they're actually tied together. They are related. And then I will also do 2 other examples following along. Okay, so let's begin. All right. Okay, the nuclear mass of helium, notice it's just the helium, it's just the nucleus and not the atom, so no electrons are involved, okay? So we have 1.0015 U, in which U is a unified atomic mass unit, which is given in your data booklet. Well, we know helium is made of 2 protons and 2 neutrons, so what we're going to do is we're going to compare the masses of 2 neutrons and 2 protons, 2 neutrons separately versus the entire nucleus of helium. So for helium, let's do it up here. This is going to be 4.0015 times whatever atomic mass unit is, and I put it up there for our convenience so you don't have to go back and forth between your data booklet. Okay, so let's do this quick calculation. I get 6.646 ... times 10 to the power of negative 27 kilograms. So I'm going to save that for now. Okay, so to calculate the mass of 2 protons and 2 neutrons, I am going to do the following. So this is 2 times P plus 2 times N from our data booklet. So this is 2 times a proton rest mass is 1.673 times 10 to the power of negative 27 kilograms. Notice it's a little bit higher than the unified atomic mass unit. And we're going to add 2 times the neutron, which is 1.675 times 10 to the power of negative 27 kilograms. Notice that's also a little bit heavier than a proton. Very interesting. So I get 6.696 times 10 to the power of negative 27 kilograms exactly. And I'm actually going to subtract the mass of our helium nucleus. So I'm going to take this guy and I'm going to subtract him. And let's see what we get. We get, 4.95 times 10 to the power of negative 29 kilograms. So it's a very tiny difference between the two. But there is a difference. And you're thinking, ideally it should be exactly the same, because a helium is essentially 2 protons and 2 neutrons. So why aren't they the same? This is where the second part of this question comes. So with a mass defect, what's happening here is that bit of mass, extra mass, that came from the proton and the neutrons are now used or converted into something called binding energy. This binding energy is what holds a nucleus together. So you're thinking, wait a minute, how is mass now equivalent to energy? That comes from the famous Einstein equation, E equals mc squared, where energy can be converted to mass can be converted into energy. And in our case, what would be the case is for a helium nucleus, once the protons and the neutrons come together, and some of that mass gets converted into this energy that holds that nucleus together. Okay, so meaning if you want to break the nucleus apart and separate them out into their protons and their neutrons, that is the mass defect, or the energy associated with the mass defect, which is the binding energy. That amount of energy you actually have to put in to the neutron, into the nucleus, to separate the helium nucleus into the 2 protons and the 2 neutrons. So we're going to use that mass defect in example 1 to calculate the binding energy of a helium nucleus. So we can do that by looking at E equals mc squared. So that mass is in kilograms, so we're going to put it in kilograms. 4.95 ... times 10 to the power of negative 29 kilograms. And C here is the speed of light. Speed of light from our data booklet is 3 times 10 to the power of 8 meters per second, and all of that squared. Okay, so we do that. We get 4.4557, which will round up to 4. Let's see. Looks like we're gonna do about 4 sig figs. 4.456 times 10 to the power of negative 12 joules. So in fact, we can even convert this into electron volts. How many? Because usually that's more applicable for us. So if we divide this by 1.6 times 10 to the power negative 19, this is how many joules there are per electron volt. This is going to give us 2.78 times 10 to the power of 7 electron volts. Or in other words, this is essentially 28 megavolts. 28 mega electron volts, okay? Or actually, approximately. All right, so that is the amount of energy released. And the amount of energy required for the binding energy of a helium nucleus, which means if you want to break a nucleus into protons and neutrons, this is how much energy you have to put in, I don't know, how you can think of it as pulling them apart, essentially. Okay, so that's it for this video. Next one, we're going to talk about some other examples with carbon-12 and radioactive decay. Thank you for watching, and Fat Mama Physics signing out.